So we're going to move on into probability. We're going to do a lot of it this week, which again means the best I can do is gloss over it and leave it up to you to kind of fill in whatever gaps you may feel that you have. So this is something that's available for you to print out if that's something that you choose to do and take notes off of. This is actually, I think it's like the first couple of pages that are in your probability packet from a way long time ago. So if you have that, you can pull it out. But really, it might be better just to print out a new copy because I've added some things. So starting out up here, you've got some basic probability rules, and they're just as important as anything else. Knowing that all of your possible outcomes can add up to 1. That kind of stuff shows up on an AP exam. So these two things are pretty important. All right, complement rule. I'm going to put a little asterisk here because the complement rule is just a great way to save yourself some time. Just remember that the complement of any event A, that A happens, is that it doesn't happen. So there are only two outcomes for A. Either it happens or it doesn't. So the two must add up to 1. So if you know what the probability of A is, then you can automatically figure out what its complement is by subtracting the probability of A from 1. That brings us to the at least 1 rule. Because if they ever ask a question where they, kind of put it to you like at least 1, what's the probability that at least one of the spark plugs goes out? Well, if you've got a 6-cylinder car and that has 6 spark plugs, well, at least 1 could be 1, but there's 6 of them. It could be 2, and you need all the combinations of 2 that could go out, then 3, then 4, then 5, then there's so many options to that why not just figure out the probability that none of them go out, right? And subtract that from 1, and then whatever the difference is will inform you as to all of those possibilities combined. So your at least 1 rule, that is the 1 minus the probability of none. Okay? All right, the next thing is your addition rule for disjoint events. And it says 2 events are disjoint if they have no outcomes in common. All right, another thing that we can use for that word disjoint is mutually exclusive. All right, so it can be put to you either way. All right, so either one of those two things mean the same thing, and that's basically things that can't occur together. All right, so can't occur together. In that case, you have a formula for it, and it's going to be or, and remember, or in probability speak means plus. So A or B, the probability of A or B is the probability of A plus the probability of B. All right? Multiplication rules for independent events. Independent, let's just go ahead and distinguish that from disjoint. This means that knowing what happens, won't inform about what happens next. All right, that's a pretty basic way to define independence. Yeah, it shows up everywhere. So if you flip a coin and get heads, when you flip it again, just because you had a head before doesn't really tell you what's coming next, right? So knowledge of what has happened does not give you any knowledge about what will happen. And this applies to the multiplication rule. So if two events are independent, then the probability that both happen is the product of the two individual probabilities. All right? In your general addition rule, your events will not be disjoint. All right? So basically, events aren't disjoint. And so you have a formula here. The probability of A or B is the same as it was up there for the addition rule, but it's minus the joint probability. Now this is general because it does work for disjoint events also. It's just that when things are disjoint, that probability will be 0. All right. Then your general multiplication rule. Oh, by the way, for your addition rule, let's just put down that to see the Venn diagram. And that's coming up. All right, for your general multiplication rule, that's whenever events A and B aren't necessarily independent. And we're going to see this in a tree diagram. Which is going to come up later too. All right, and you're going to know if you have this term here, which is a conditional term, B, given that A occurred, when you get the words if, when you get the phrase given that, and there's some other ones, but those are the two that occur most frequently. And just remember that you can take this formula up here and you can rearrange it algebraically to figure out what your conditional probabilities are. All right, so these are actually things that show up a lot too. To look at things with symbols, remember this upside down U looking thing is your intersection or and, so that's intersection. And hang on just a second. All right, so here is the next page, and here's just more symbolism. The symbolic shortcut for or is union. So this refers to union of A or B, and it just means that it could be A, it could be B, or it could be whatever they share. This represents your terminology. And I don't know that there's anything here that I need to elaborate on, so I'm just going to move on. If you see any term here that requires your attention, I will leave that up to you. All right, so looking back at the general addition rule, this is kind of an example using a Venn diagram. So you've got a survey of couples in a city, found the probability that the husband employed is 0.85. So a good thing to do with these things is to just define these variables. So event A is that the husband is employed. Probability that the wife is employed is 0.6, so I'm going to call that event B, is that the wife is employed. All right, and they also give us the joint probability of 0.55. So we're supposed to find the probability that at least one of them is employed and that neither is employed. Okay. Remember how we handled Venn diagrams? You work from the inside out. So I'll call this circle, this whole circle, is event A. That's for the husband. And this circle, this entire one, is event B, and that's for the wife being employed. So where they overlap, right in there, is A and B. And let's put in that probability. That probability is 0.55. Okay? So if you look at this Pac-Man looking part, that's really where the wife is employed without the husband. So that's A and B complement. And the whole thing is A, whether it's with the husband or without. So the wife alone is just going to be whatever the difference is between 0.55 and 0.60, which is 0.05. Oops, I don't know why that went a little haywire. Let's see if I can get rid of it. All right, so 0.05. So the whole thing is 0.6, but the wife alone without the husband is 0.05. And then over here, the entire one for the husband is 0.85. We know that part of that is him working when his wife is working. We just want to know what it is when the wife isn't working. Just the husband alone. So that'll be 0.85 minus 0.55 is 0.3. All right? So at least one of them employed would be that A is employed, B is employed, or both are employed. So that'll be 0.05, 0.6, 0.9. Right? So we can just list that as being 0.05 plus 0.55 plus 0.30, which is 0.9. And then neither of them is employed. That would be here. This is A complement and B complement. And the whole thing, whoops, left out my B. Hang on, let me get rid of that. All right, so A complement and B complement. Let's get this right. And that's got to be what's left over, because the whole thing has to add up to 1. So that's 0.10, which is 1 minus your 0.90, or 0.1. All right? So there's your Venn diagram. The next thing on the agenda is tree diagrams. So all right, so here's a tree diagram example, and we're going to also try to throw this into a table. So, marketing manager of a toy company is planning to introduce a new toy for the holiday shopping season. In the past, 65% of new toys introduced by the company have been successful. Before the toy is actually marketed, research is conducted and a report, either favorable or unfavorable, is compiled. In the past, 70% of the successful toys received favorable reports, and 20% of the unsuccessful toys also received favorable reports. All right, what is the probability that the new toy will be successful if it received a favorable report? So let's just start out with defining variables, because that's always a good place to start. So A is going to be the event that a toy is successful. And event B will be the event that it received a favorable report. Okay, so you can kind of start wherever you want, but let's just go ahead and make a split here. And we'll make a split here. This will be success for the toy at the holidays, or not. This is the probability of A, and that should be given to us 0.65. And so since both of those are either successful or they aren't, this is the probability of A complement. That has to be 0.35, because the two have to add up to 1. All right, so let's further split this off like so. This will be a favorable report, and this will be a not. And we can split this off the same way, favorable or not. All right. It says that in the past, 70% of successful toys, so given that the toy was successful, received a favorable report. All right, so that'll be the probability of B given A, and that should be 0.70. And this will be the probability of getting an unfavorable report. Right, that's B complement given that the toy was a success, and that should be 0.30 because that's the only two things that could happen. All right, this should be the probability of B given A complement, right? Wasn't a success, but it received a favorable report. That should be, let's see, 20% of the unsuccessful toys receive favorable reports, so that's going to be 0.2. And this should be the probability of B complement getting an unfavorable report given that the toy was unsuccessful, and that'll be 0.8. All right, so that should add up to 1. If you then travel along these branches, you can get all the joint probabilities, all right? So this will be the probability of A and B, and that's the product of these two, so that'll be 0.455. Check these. This will be the probability of A and B complement, and you just go here down to here. 0.65 times 0.3 is 0.195. Go this branch, this will be the probability of A complement and B, and that comes out to 0.07. And then traveling down this last branch, this will be the probability of A complement and B complement. And if you multiply 0.35 times 0.8, you get 0.28. And so all of these should add up to 1. So these add up to 1, these two, and these two should all add up to 1. All right? So what are they asking us? The probability that the new toy will be successful if it received a favorable report. I believe that should be the probability of A given B. Right? Has that word if, so it's definitely conditional, but it can't be B given A. It's got to be A given B. All right, that had a formula. This is the probability of A and B divided by the probability of whatever's sitting here. That'll be the probability of B. All right, A and B is this number here, so that'll be 0.455. Now the probability of B was not given to us. Right? We knew the probability of A, but not the probability of B. So the probability of B can happen two different ways. It can occur jointly with A, and it can occur jointly with A complement. So really, it's the sum of these two things that go in the denominator. So that'll be 0.455 plus 0.07, and that should give you I put it right here, 8667. So there's the answer. Now, a lot of you guys don't like tree diagrams. You prefer these things here, and I don't blame you. All right? So let's go ahead and pretend we had never worked that problem. And we'll just start out. This will be the probability of A. All right? And that'll be 0.65. This will be the probability of A complement, and this will be 0.35. Right? Keep in mind that everything here has to add up to 1. Right? That's like a grand total. So probability of B would be here, and this will be the probability of B complement. All right? So let's see. What we need is a joint probability, one in this column and one in this column. All right? Preferably catty corner so that we can fill everything in. All right? So let's go ahead and let's tackle this right here. All right? Keep in mind that we need the probability of A and B. So this will be the probability of A and B. So we need to work with a formula on that one. So the probability of A and B is going to be the probability of A times the probability of B given A. And we know those things. The probability of A was 0.65, and the probability of B given A was 0.7. So that joint probability should be 0.455. That should look like a familiar number. All right, if you then subtract that from 0.65, because the two here have to add up to each other, this will be 0.195. All right, so then we can go ahead and fill in, let's say, this one, probability of A complement and B. All right, so the probability of A complement and B, that'll be the probability of A complement, which we happen to know because it's the complement of 0.65, so that's 0.35, times the probability of B given A complement. All right, and that should be 0.2 because we were given that up here. See if we can find it. Remember the 0.2, the 20%? That's this, and that's this. All right, and so that product, get my pen squared away here, that product should be 0.07. All right, so that's 0.07. Subtract that from 0.35, this will be 0.28. And if you add across, this is 0.525. That's your probability of B. If you subtract that from 1, you get 0.475. And they're asking us for the probability of A given B. And that'll be the probability of A and B. Wow, my pen's getting a little out of hand today. All right, let's see if I can't get this right. All right, and that's over the probability of B. All right, probability of A and B is this. So 0.455. And the probability of B is this, 0.525. And you'll get the same thing, 0.8667. So however you want to do it, it's fine by me. All right? So I'm going to change again to another screen. All right, the very last thing that we're going to look at is simulation. I'm not exactly sure how much you'll see on the AP exam for simulation. It has shown up there. All right, so let's just, treat it like they could ask it. All right, so suppose the probability that an exploratory oil well will strike oil is about 0.2. Conduct a simulation to answer the following questions. Assume that the outcome, oil or no, for any one exploratory well is independent of outcomes from other wells. Use the random number table below and conduct 20 trials. All right, I didn't even put a random number table here. We're just going to do random integer, okay, from the calculator. So first we have to assign digits, and since this is 20% without any more detail, we can just say that the numbers 0 and 1 will represent striking oil. And then 2 through 9 will represent failing to strike oil. So fail to strike oil. And we can just do random integer 0 through 9. And they want us to conduct 20 trials, so 20. And I'm getting that strange, I don't know, my equipment is really acting weird. All right, now it's better. Okay, so let me show you how I did this on the calculator. It's real quick. So here it would be open, and let's just go down and open up a spreadsheet. And we're just going to leave that as A, and we'll put in a formula. So this will equal, and I'm going to go to the book. Here's the book right below delete. And I'm going to go down to R. So go ahead and hit R here. And let's see what we can find out, right? Random integer is right here. So let's go ahead and hit enter. All right, and so we need the range of numbers. So 0, comma, 9, comma, and then how many we want. And it should fill in this column with 20 random numbers from 0 to 9. Hit enter, and there they are, okay? Now, what I'm going to do is, I did this earlier, and so the rest of my notes here are based on what I did earlier. So I want those things to match, all right? So let's see, outcomes. All right, so this is, let me make sure I have this right, and it might actually end up being the very same thing that came up. A 9, a 9, 1 and a 5, 4, 7, and 0, and then 3, 9, 2, and 7, 9, 2. I'm not even going to correct that. 7, 9, and 2. One of these days I'll figure out why it's doing that. 3, 0, 9. 1, 0, 5, 8. Right, so there are my 20 attempts. And let's see. This one was striking oil. This one was striking oil. This one was striking oil. This one and this one. So I got 5. All right. So what should we have expected? Well, let's see. 20 times 0.2 is, well, let's check it. So we'll go to the home screen, open up a calculator page. So 20 times 0.2, we would have expected 4. All right. So let's see. This is 5 out of 20. So the probability that we simulated was 0.25. All right. So estimate the average number of wells that need to be drilled in order to strike oil. All right. That sounds a lot like geometric. All right. And I'm working off of my value that I received through simulation because it's when you first strike oil. Right. So this is going to be probability of striking oil. Is 0.25. That's what I figured out here. This we said was geometric. And if you recall, and this is a little bit of a glimpse in tomorrow's material, mu equals 1 over p, which is 1 over 0.25, which is 4. Interesting. Then it says, what is the probability that it'll take fewer than 3 attempts to strike oil? Again, that's for a first strike. So this is going to be geometric. And I'm just going to do it with calculator speak. 0.25. And it's either going to be 1 or 2 because you can't strike oil if you don't drill a hole. And you get 0.4375. And what is the probability it'll take exactly 6 wells? Actually, I'm sorry. Fewer than 3 attempts would be, let me fix this, geomet CDF. All right, I left off the CDF, my bad. All right, because it's where it's a range of numbers. So the values that go in here are the probability lower bound, upper bound. This here, exactly, the word exactly is PDF. So this is Geomet PDF, and this will be 0.25, and then just the exact amount would be 6. It's not really a range of numbers. And this will be 0.059326. All right, so we covered a whole bunch of stuff for probability today.